The topic I'm presenting today is de-randomizing MCMC dynamics with the diffusion Stein operator, which is a work jointly done by me and my two supervisors. As the title suggests, we focus on the Bayesian sampling of our normalized distributions. We intend to infer from a distribution with an unknown normalization constant z, and we only have access to the energy function u. Many approximate Bayesian inference methods are essentially optimizing within a set of distributions. For example, MCMC sampling algorithms extract samples by simulating a stochastic Markov chain, whose stationary distribution coincides with the target distribution. Variational inference finds within a set of parametric distributions the one that closely resembles pi. We intend to find sample-based deterministic algorithms with similar behaviors of MCMC sampling. We focus on MCMC dynamics, a specific subset of MCMC sampling that can be represented with a stochastic differential equation. Such diffusion processes take two parameters, a positive semi-definite matrix-valued function A that parameterizes the diffusion term, and a skew-symmetric matrix-valued C. The drift term is a combination of the gradient of the log likelihood and the divergence of A and C. A simulation of two examples of such SDEs is shown in the plot below. As we can see, the single sample of the Markov chain takes highly stochastic paths, but eventually approaches the target distribution. The first step of turning such processes into a deterministic system is to change an SDE into an ODE, which can be done with investigating its Fokker-Planck equation. If we know the marginal density of xt at each given moment, the ODE below simulates the same evolution of densities as the original MCMC dynamics. This approach relies on an estimate of the log likelihood at each moment, which is a highly non-trivial task. We intend to address this problem by internalizing the estimation process. We present a simple solution of projecting the drift term of the ODE onto a reproducing kernel Hilbert space, which in turn gives a sum of two expectations with regards to rho t. The first is a weighted average of the MCMC drift term, and the second term is a repulsive force. The summation of the two terms coincides with what is known as the diffusion Stein operator. By keeping track of a set of samples, we can naturally estimate the sample estimates with Monte Carlo integration. The plot below visualizes the drifts of each particle given different MCMC parameterizations. Our method is a generalization of what is called the Stein variational gradient descent, which can be seen as a de-randomization of the simplest Langevin dynamics. We extend this framework to emulate the evolution of all MCMC dynamics, as shown by the de-randomization of the stochastic gradient Hamiltonian Monte Carlo on the right side. We present the efficacy of our method with the application of task-specific Riemannian parameterizations that draws deterministic samples from a multimodal distribution, as shown by the plots of our method effectively exploring the space of distributions and finding a high-quality sample representation of that. We demonstrate in this presentation a simplified derivation of how to de-randomize MCMC dynamics. For a more comprehensive view and experiments, please check the preprint version of our paper.